Welcome to Lecture 6, which deals exclusively and completely with circular motion. Circular motion is one of the most important types of motion throughout the universe, in technological devices, in nature, in atomic-sized systems, in planetary systems, in galactic systems throughout the entire universe. Circular motion is ubiquitous. So I want to spend the entire lecture on circular motion, and the first thing I want to say about circular motion is that it is accelerated motion. It's accelerated motion because even if circular motion occurs at a constant speed, a situation called uniform circular motion, the motion is nevertheless accelerated because it's motion whose direction is continually changing. So never forget, circular motion is accelerated motion. Anytime you see something moving in a circle, you know immediately that it's accelerated. My tennis ball here is moving in a circular path in the vertical plane. I could equally well whirl it in a circular path in the horizontal plane or somewhere in between. These are both examples of circular motion. And if the speed is the same all the time, it's uniform circular motion. If there were a little speedometer attached to that ball, it would read a constant value, it would read a constant speed, but that would not mean the motion was not accelerated. The motion is accelerated because the direction of the motion is continually changing. Circular motion is accelerated motion. Let's take a look at some other examples of circular motion. Circular motion, as I've indicated, is ubiquitous. So here are some examples. You see a car and you see its wheel turning. It's heading around a curve in a road. Two things are actually happening here. The wheel is turning. There's circular motion of the wheel itself. And the entire car is turning as it rounds that bend. Two circular motions happening here as the car turns the corner. It is accelerating. The wheel is accelerated because of its spinning motion. The entire car is accelerated because its motion is not in a straight line. And even if the driver is holding the speed constant at 55 miles an hour or whatever it is, it's still accelerated motion. We've got an airplane. It's undergoing what's called a bank turn. We'll see later why airplanes have to bank in order to turn. The frame is fixed on the airplane, so watch the ground to see that this airplane is undergoing a turn. That's circular motion. You see an old-fashioned analog clock. Its hands are undergoing circular motion. The tip of the minute hand is undergoing a circular motion with a certain constant speed. The tip of the hour hand is undergoing circular motion with a different constant speed. That depends in part on how long the hand is and how long it takes to go around, 12 hours versus 1 hour. The second hand is also undergoing circular motion. These are all uniform circular motions if it's a good clock because they're happening at a steady rate. We see a simulation of an electron circling around the nucleus in an atom. Now, much later, when we start talking quantum physics, we'll see that's not really a very good picture of an atom, but it's still a useful picture. And in this atom model, uniform circular motion is occurring, and our understanding of that atom will be enhanced by our understanding how that circular motion works. In the middle, we see a simulation of the Earth going around the Sun. The Earth's orbit is almost a perfect circle. It's about 3% off. It's slightly elliptical, but it's close enough that we can consider this basically a case of uniform circular motion. And finally, here's an everyday thing, a bicycle. The bicycle is going, in this case, in a straight line, but the wheels and the pedals are undergoing circular motion. Pick a point on the wheel, pick the valve stem where you insert air, and that's going in a circular path. Look at one of the feet on the pedal, and it's undergoing circular motion. Circular motion is ubiquitous, and circular motion is accelerated motion. And circular motion is occurring whether or not we're going in a complete circle or just part of a circle. So you're driving down a straight road and you come to a big 90-degree bend. While you're in that bend, you are undergoing circular motion. And if you're in that bend and driving at constant speed, you're undergoing what I'm calling uniform circular motion. And the first half of this lecture or so, a little more, will be concentrated on uniform circular motion. And then we'll look at the slightly more general case and slightly more complicated case of non-uniform circular motion. So for now, I'm talking about uniform circular motion, motion in a circular path, fixed radius to that path, a real circle at constant speed. It doesn't have to be a complete circle, though, as long as it's a circular path. Circular motion is ubiquitous. Now, I've said over and over already that circular motion is accelerated motion. In previous lectures, we've seen the definitions of velocity and acceleration and how we carefully built up those definitions by talking about velocity as the rate of change of position and acceleration as the rate of change of velocity. We first did it in one dimension, and then we did it in multiple dimensions as vectors. Now we want to understand circular motion, first uniform circular motion, in that same context. So when I say circular motion is accelerated motion, you might think, well, how am I going to measure that accelerated motion? What are the units of acceleration? Their rate of change of velocity over time. They are rate of change, delta v, over rate over time interval involved, delta t. What are the units? Meters per second, or meters per second squared. And that may sound a little bit odd when we're talking about circular motion, but nevertheless, we want to quantify the acceleration in circular motion, and we want to say this velocity is changing at the rate of so many meters per second, so many meters per second squared, even if the number of meters per second, the speed, is itself not changing. We can still characterize the acceleration, which, remember, is not defined as the rate of change of speed, but the rate of change of velocity, a vector quantity. We're going to characterize acceleration in circular motion in terms of how many meters per second, the velocity, not the speed, but the velocity is changing. And so we're going to spend a good part of this lecture at our big screen doing the math to describe uniform circular motion rigorously and mathematically. So let's go there. First of all, just one other example of uniform circular motion. Here it goes. Got a ball going around in a circular path. How do I characterize that motion? Well, I need to know the radius of the path, and I need to know the speed of the ball. Again, speed is different from velocity, so let's take a little bit of a closer look at this situation. Here goes the ball around and around. So I'm going to attach a velocity vector to it. That describes its velocity. And instantaneously, when the ball is at the top of that path, it is moving to the right. And so the velocity vector is instantaneously pointing to the right. As the ball goes around, you will see that the velocity vector changes direction. It's always, in fact, tangent to that circular path, and around it goes, tangent to the circular path. There it is. The velocity vector is attached to the moving object, and the velocity vector is tangent to the circle, so the object's direction of motion is always changing, the direction of its velocity vector is changing, and any change in velocity, whether in direction or magnitude or both, is by definition an acceleration. So this is accelerated motion, and you can see it vividly right there when we've attached the velocity vector, because you can see that the direction of the velocity is continually changing. And I want to describe that change in terms of meters per second of change, not in speed, because the speed is constant, but in velocity. So how are we going to do that? Well, let's take a closer look. Here's a picture of the same situation we just saw, and what I'm showing you is the position of the ball when it started out, and the position of the ball a little while later. A couple things you'll notice. First of all, the two velocity vectors have exactly the same length. They represent the same speed. They are different velocities because they're pointing in different directions, but they represent motion with the same speed. The ball has moved a little bit from its initial position, and I'm going to describe the change in its position by this angle designated by the Greek theta, which we will commonly use throughout this course for angles. And because this is uniform circular motion in a perfectly circular path, the distance from the center of that path is the same for both positions of the ball, and I'm designating that by that lowercase r. That's the radius of the circular path. So that characterizes everything I need to know. The velocity and its speed or magnitude v, the radial distance r, and the angle theta through which the ball has moved in the time I'm considering. So this, again, is a snapshot at two different times as this ball continues in the circular motion we saw before, with the velocity vector going along with it. And the velocity vector, notice, is always tangent to the circle, and that means it's at right angles to this radius from the center to the point where the ball is. So the velocity vector is at right angles to the radius. That's going to be important in the geometry we're doing here. So let's work on this geometrically. There's the first velocity vector. I'll call it v1. It's a vector. It's got an arrow over it. That's why it's a vector. That's how I can tell it's a vector. There's the velocity v2. Now remember about vectors. A vector cares what its magnitude is, and it cares what its direction is, and that's all it cares about. You can slide a vector around, you can move a vector any way you want, put its tail anywhere you want, provided you don't change its length or its orientation, that is, its direction, but you can move it in space. So I'm allowed to take v1 and put it up here, and I'm allowed to take v2 and put it tail to tail with v1, and I haven't changed either of those vectors, because all a vector cares about is its magnitude and direction. Now, if I started with v1, and I wanted to make it into v2, I would have to add this little bit of a vector here. Or put it another way, if I subtracted vector v1 from vector v2, this would be the change between the two of them. I call that change delta v. Delta v is the final velocity minus the initial velocity, or equivalently, it's what I have to add to the initial velocity v1 to get the final velocity v2. So there's delta v. So I now have a new vector introduced. That's the change in the velocity between when the ball was at this position and when it was at this position, and that is the clearest indication that we're dealing with accelerated motion. Because if there were unaccelerated motion, if we had no acceleration, those two velocity vectors would sit right on top of each other and they'd be the same. This is accelerated motion. Circular motion is accelerated motion. There's the clue. We have a delta v. As time goes on, the velocities are not the same, and there is a measurable change between them. And we want to measure that change because we need to know that change, and we need to divide that change by time in order to figure out exactly what the acceleration is. That's the name of the game here. We want an acceleration in meters per second for this situation. Okay, now let's look at this little piece of the geometry here involving those two radii and that angle. So let's pull them out. Here are the two radii. They're of equal length because it's a perfect circle. There's some angle theta between them. And what I want to point out is that because the two velocity vectors are at right angles to the two radius vectors, the angle between velocity vector v1 and v2 is the same angle theta. That's because the angle between this blue velocity vector and this radius is the same as the angle between this blue velocity vector and this radius, and so that angle is the same as that angle. In fact, in the limit of very small thetas, very small times, both those would go to zero. If we got around to 90 degrees, you can see the two vectors would also be 90 degrees apart. So those two angles are the same. So let's now look at these two almost triangles. Let's make that one a triangle also. So now I have two triangles. And I'm going to claim that the length, the little short side of this triangle, has a length approximately, not exactly, v, the speed at which this ball is going around in its circle, times delta t, where delta t is the time interval between when the ball was here and when it was here. Why do I say approximately? Because the ball is really moving on a circular arc. And the length of that circular arc is, in fact, exactly v delta t, because that's the path it's actually taking. But look at this little segment here. That's almost the same. And you might say, well, almost isn't good enough. Well, it is good enough if I imagine this angle shrinking ever smaller. That's the process that calculus would use. And I'm actually skirting around calculus here without actually getting into calculus. But calculus would make the argument that in the limit that that angle gets very small, these two things become indistinguishable. And ultimately, in the limit that that angle goes towards zero, they become the same. So I'm going to say that this segment is approximately v delta t. And then in the very end of this whole process, I'm going to argue that if I make delta t very small, so the angle becomes correspondingly small, that has become an exact result. So we'll carry that result through, and we'll make that argument a little later on. So we'll take that circle away, and we'll notice now that we have two triangles. And those two triangles have, they're isosceles triangles. They have equal sides. Equal sides. I've still labeled these v1 and v2. By the way, notice that I've taken the vector signs off because I'm now going to talk about the lengths of the sides of triangles, not about vectors. So I really could have taken off the 1s and 2s also, but I want to remind you we're dealing with lengths of two different velocity vectors, or magnitudes of two different velocity vectors, or speeds associated with two different velocity vectors, but those two speeds are the same. So I could have just called it v, and I'll soon do that. V. V is the same as v1 or v2 without the vector sign, because all that matters then is speed, not direction. Now look at these two triangles. They're isosceles triangles, and they have the same angle. And that means they're similar triangles, like you learned about in 10th grade geometry. And if we have similar triangles, we know that the ratio of the short side of this blue triangle to the length of either of its other sides, they're equal, and they're equal to v, the speed, is the same as the ratio of the short side of this white triangle to either of its sides of length r. So delta V over V is, and I've used approximately equal because of that funny business about the circular arc not being quite equal to the line. So there's an almost equality there, and it's going to become a perfect equality when we let that angle get very small. So what's the acceleration? The acceleration is delta V over delta t. Acceleration is defined as the rate of change of velocity. Here's the change in velocity that occurred during the time interval delta t when the ball moved from this position to this position, and we found that that's approximately given by v squared, the square of the speed, divided by the radius of the circular path. Almost approximately. In the limit that theta gets very small, that will become exactly true, and that will be the instantaneous value of the acceleration, and you can calculate that given the speed and the radius, and that number has the units of meters per second, meters per second squared, even though the number of meters per second isn't changing. This is about the rate at which the velocity is changing, and it's changing entirely in direction and not at all in speed. So there is our acceleration formula. Let's look in a little bit more detail now. There's our blue triangle. There it is blown up so we can look at it big, V1, V2, and delta V. And now let's make that angle very small. I've already argued that as the angle becomes very small in our white triangle, that little short side became equal to that segment, or that curved arc, and the approximate equality becomes exactly equal. I want to point out something else that happens as this angle becomes very small. As that angle becomes tiny, remember, the angles of a triangle add up to 180 degrees. As that gets almost to zero, these two angles, which are equal because it's an isosceles triangle, both go nearer and nearer and nearer to 90 degrees. And that means that delta V becomes essentially at right angles to V itself. And in fact, that's what happens anytime you have a change in direction but no change in speed. In that case, the change in velocity and therefore the acceleration is at right angles to the motion itself. And that's what we're seeing happens here. So the acceleration in circular motion ends up being at right angles to the motion itself. Let's just take another look at that. Here's the picture now. We've concluded that the acceleration is given by v squared over r, square of the speed over the radius. I'll show you in a minute why that has to be. That's a measurable quantity in meters per second squared. And we know something else about the acceleration. We know its direction is toward the center of the circle, and for that reason it's called centripetal acceleration. Not centrifugal. That word is banned. But centripetal, which is also a word that can cause confusion, but I'm at least going to use it, it means toward the center. The acceleration points toward the center of the circle, and as the ball goes around in its circular path, there it goes. Its velocity vector is always tangent to the circle, and its acceleration vector is always at right angles to the velocity vector and directed toward the center of the circle. So we know everything about this acceleration. We know its magnitude and we know its direction. Its magnitude is v squared over r. Its direction is toward the center of the circle. And I can't emphasize how important this is. We're going to analyze the orbits of planets using this. We're going to analyze the hydrogen atom using this. We're going to analyze mundane situations like loop-the-loop roller coasters using this. This is a really crucial formula, a very simple one in physics. It describes the acceleration when we are in circular motion. So there's the centripetal acceleration. Now, let's just take a look at a picture that makes this a little bit more real. Here's a picture of a truck on what's obviously a curved path. The truck is going around the curved path. The driver may see 35 miles an hour on the speedometer and 35 miles an hour the whole time, but as I've argued, this is accelerated motion, and there's the direction of the acceleration vector. It's toward the center of the circle. As we'll see later when we talk about forces, there better be something to push it in that direction, and that something is going to be the friction between the tires and the road. This is a centripetal acceleration toward the center of the circle. It's the acceleration of an object in a circular path. And let's just take another look at that equation and see if we can understand why it has the structure it does. So here are two circular paths on which two different objects are moving with equal and constant speed, so they're both in uniform circular motions. But one of those paths is bigger. Now, a while later on the smaller circle, the object will be moving straight downward. There will be a certain change in its velocity, the difference between those two vectors. A while later on the big circle, and a longer time than it took for the small circle, because the speeds are the same in both these cases, but the big circle is bigger, there will be a downward motion of the object on the bigger circle. And the difference between those two velocities is the same in both cases, because they're two velocities of equal magnitude at right angles. But for the bigger circle, it took longer, and that tells us that the rate of change of velocity is less, and therefore the acceleration should be less for a bigger circle. Not surprising. That's why the 1 over r appears in the denominator of that equation. On the other hand, if we look at two equal-sized circles with different speeds, we can also understand why this formula has the structure it does, in particular why it's got v squared upstairs. So now the upper circle has a certain speed, a smallish speed, and there is a delta v, which is the vector difference between those two vectors, the one going horizontal and the one at right angles. And if you work it out, you'll see that's the vector you have to add to the top one to get the downward pointing one. On the other hand, on the lower circle, which is the same size circle, delta v is bigger because v itself is bigger. So we expect that the acceleration will be bigger if the speed is bigger. Yeah? But why v squared? The reason for the v squared is there's something else happening on the lower circle. The lower circle, remember, v is bigger. The speed is bigger, and so it's going to take less time for the particle to move from when it's going to the right to when it's going downward. And so those two effects, a bigger delta v and a smaller delta t, combine to give an acceleration that's proportional not to v itself, but to v times v to v squared. So there's a motivation of why we're dealing with an acceleration which is v squared over r. Well, let's talk briefly about what happens if the motion is non-uniform. We could have a situation where the speed of an object is changing even as it undergoes circular motion. Well, in fact, it's convenient in that case to think of two components of the acceleration. There is a radial component pointing toward the center of the circle, and that's associated in this picture of a car going around a turn with changing only the direction of the motion. And then there is a tangential component, a component that's along the direction of the circle, and that's changing only the speed. And as you can see here, the net acceleration, which is pointing sort of down and to the right, is the sum of those two vectors. And you can also see in this case, because the tangential acceleration, the one that's parallel to the local direction of the tangent to that path, is pointing opposite the velocity, this car is in fact braking. It's slowing down even as it goes around the turn, and the brakes are providing the slowing down acceleration, the tangential acceleration, and the tires are ultimately providing that, and the tires are also providing the acceleration that changes the direction. So we can have non-uniform circular motion in the sense that speed is changing as well as direction, but we can still analyze it using what we understand of A, straight line acceleration, and B, acceleration in a circular path, the acceleration that we now know has magnitude v squared over r. We could also be moving, as this car is, in a situation where the curvature of our path may be changing. That's non-uniform circular motion due to a changing path curvature. It's also due, possibly, to changing speed. The driver could be driving along here at different speeds. And at each point on that curved path, we can define something called an osculating circle. It sort of means the curve and the circle are kissing. They are exactly matched right at that point. If you want to get really profound about it mathematically, if you've had calculus, not only are their derivatives equal there, but their second derivatives are equal there. And so they are very closely matched. And that defines a radius, a local radius of curvature of that path. And that's what you use for r in v squared over r. And locally, at the instant the car is at a certain point on the path, it's got some speed v, and that's what you use for v. So the acceleration may be changing in magnitude as you go around. By the way, one thing I should also point out about acceleration in circular motion, and you saw it in the diagram here where the acceleration vector was going around, although the acceleration has the same magnitude, v squared over r, when the motion is uniform and circular, it is not a case of constant acceleration. It is not constant acceleration because the direction of the acceleration vector is changing, just like it's not constant velocity because the direction of the velocity vector is changing. Circular motion is never motion with constant acceleration. It may be motion with constant speed, but it's never motion with constant velocity. So there's non-uniform circular motion. Let's do an example on our big screen of what we can do with this fact of circular motion and acceleration equal to v squared over r. So I'd like to consider a situation that often people who are suggesting we build space stations that astronauts would stay in for very long times, we could make a kind of artificial gravity equal to the gravity at Earth's surface. That is not the case with the International Space Station, but a space station that was built in the shape of a ring like this could be set spinning. And at what rate would it have to spin so that somebody walking around the rim, like you see these people doing, would experience the gravity equivalent to that at Earth's surface? Why do they experience any gravity at all? Because if they're standing still on that rim, they are in uniform circular motion and they're being accelerated toward the center. And if that acceleration has the right magnitude, it will feel exactly like they do here on Earth. So we want v squared over r to be g, the acceleration of gravity at Earth's surface. We solve that for v. V is the square root of rg. Nothing in here about mass, by the way, which is good because it will work for everybody. The time t for one revolution of this thing is 2 pi r over v. I'm just going to work this out and get an answer in terms of how many spins it must do every second or minute or whatever. I'm going to substitute for v. V is square root of rg, so that v downstairs becomes root rg, and the r upstairs not inner root divided by the r downstairs inner root gives me an r upstairs inner root. So there's basically the answer for t. Do the numbers. R is 225 meters. That's half the diameter I've shown there, 450 meters. G is 9.8 meters per second squared at the surface of the Earth. And I get t equals 30 seconds. So this thing needs to spin at twice per minute, and it will produce artificial gravity. It's not gravity, but it simulates the effect of gravity. And way on in this course, when we get to general relativity, that's going to come back to haunt us, this sort of ability of acceleration to mimic gravity. But there it is, that space station, walking around the outside of it. The astronauts in that space station would feel just as they do here on Earth. And if they jumped up, they would accelerate downward, at least locally, with acceleration 9.8 meters per second squared. And if they stood on a scale, they would apparently weigh exactly what they do here on Earth. So there's a simple example using that fact of acceleration being v squared over r. Well, let's wrap up. Circular motion we've seen is ubiquitous. It occurs on atomic to galactic scales, and everywhere in between, including lots of cases in the everyday world, like airplanes and cars and bicycles and watches and you name it. Circular motion is accelerated motion. The magnitude of the acceleration is v squared over r. The direction is toward the center of the circle. It is not motion with constant acceleration. It's motion, if it's uniform circular motion, with constant magnitude of its acceleration, but the direction is always changing. So never use one of those constant acceleration formulas to describe circular motion, because it isn't constant acceleration. It's got constant magnitude, but not constant direction. And finally, we looked at non-uniform circular motion, in which we have changing speeds as well as changing curvature. So we know quite a bit about circular motion. In fact, we know basically everything we need to know to do a lot of physics with it. Now, you can stop there if you want, but let me give you a challenge, in case you'd like to do a little more math. So here's my challenge. I've got a jet plane. It's diving vertically downward at a high speed of 1,200 kilometers per hour. The pilot can withstand a maximum acceleration of 5 times the acceleration of gravity, 5 Gs, before blanking out. And that happens because the acceleration affects the blood flow to the brain and you black out. And it's going to be dangerous if you're flying a plane, especially at 1,200 kilometers an hour. So you want to avoid that. So here's the question. Zooming straight down, what's the minimum height above the ground at which the plane can begin to pull out of that dive and execute a quarter turn, so it's going horizontally and maybe then back up again, without the pilot blacking out? What's the answer? Important to know if you were that pilot. Okay, here we are. As you can see in the diagram, what's going to happen is I'm going to start that turn, I'm going to undertake a quarter turn, and the radius of that quarter turn is the distance above the ground at which I have to start making the turn. Let me call that distance h. So the height h is the radius of the quarter turn. That's the answer I'm looking for. We know what the acceleration is. It's v squared over r. So that's v squared over h because the radius is h, and we want that to be equal to 5g because that's the maximum we can have. And of course, we're going to have to back off from the final answer just a little bit to give a margin of safety, but there we are. We want it to be 5g, so let's solve for h. H comes out v squared over 5g. I'll let you do the conversion. You got to work in SI here. Convert v from kilometers per hour to meters per second and do the numbers, and you will find out that h had better be 2.3 kilometers. So you better start that turn at least 2.3 kilometers above the ground. If you don't start it that high, you're going to be too close to the ground. You're going to have to speed up and make an even tighter turn, and then you are going to be blacking out. So you don't want that to happen. So start at least 2.3 kilometers above the ground.